Welcome back. Resuming where we stopped last time, we defined a set, properties of a set, and real-valued set. So this is a summary of real-valued set. We are talking about a set of real numbers, which is a set of all numbers in the universe, also regarded as the universal set. So it is divided into irrational numbers and rational numbers. Under irrational numbers, we have non-recurring and non-terminating numbers, which cannot be expressed in fraction form, can only be expressed either in surds or decimals. Examples can be square root of 2 or pi. And the set of rational numbers is a set of numbers that can be expressed in a fraction form. A over b, where b is not equals to 0, where a and b are just integers. So rational numbers can be classified as fractions. We have proper and improper fractions, or decimals. We have terminating and recurring decimals. We also have integers. So under integers is divided into even or odd numbers, which can either be classified as negative integers or a set of whole numbers. So negative integers, as I said, they are numbers that are less than 0. As for whole numbers, are numbers starting from 0 going upward. So it's divided into 0, a set of 0 integer, and also a set of natural numbers. So under a set of natural numbers can be classified as composite numbers and prime numbers. And the business of the day is now moving on to set operations. Conjunction, disjunction, complement, and product are the basic 4 operations in sets. Let A, B, and C be sets in the universal set U. Then we define the following. Intersection of two sets A and B is a set containing same or common elements from both sets A and B. Is given by A intersect B, so which is defined by X, an element of the universal set, such that X is in A intersect X is in B. If A intersect B is empty, then A and B are disjoint sets, meaning they have nothing in common. They have no common element. Also note that this set is not empty. It's just a singleton set containing an empty set as an element. Secondly, we define the union of two sets as a set containing elements from either B or C or both. Is given by B union C, which is defined by X, an element of the universal set, such that X is an element of B or X is an element of C. If B union C is actually the universal set, then B and C are complementary sets, meaning they are the only sets in the universal set. And so, for you to understand what we mean about complementary sets, let's first define complement of a set. Complement of a set A complement, meaning not A, is a set containing elements from the universal set that are not in A, given by A complement, which is the universal set minus A. So is given by X an element of the universal set such that X is not in A. X is actually in A complement. So for complementary sets B and C, we have B complement, which is the universal set, minus B, which is in fact C. And C complement given by universal set minus C, which is also B. So that's what we mean when we say B and C are complementary set. The complement of B is C and the complement of C is B. Cartesian or cross product of two sets A and B is a set of an ordered pairs of elements. A pair can be X, Y and Y, X, with X an element of A and Y an element of B. So our cross product can be given by A cross B, which is defined by a pair XY such that X is an element of a set A and Y is an element of a set B. And B cross A, which is defined by Y, X such that Y is an element of a set B and X an element of a set A. Note that A cross B is not the same as B cross A. An example. Suppose your set A is given by three elements X1, X2, X3, and your set B is given by two elements Y1 and Y2. A cross B will be a pair X1, Y1, X1, Y2, X2, Y1, X2, Y2, X3, Y1, and X3, Y2. And for B cross A, so now we are starting with Y1, X1, Y1, X2, Y1, X3, Y2, X1, Y2, X2, Y2, X3. So this is the result. If you can see that indeed A cross B is not the same as B cross A. Moving forward, set laws. Untitled laws. If we take a union of any set with an empty set, we'll get that set. An intersection of any set and the universal set will get that set. Domination laws. A union of any set with the universal set is the universal set. An intersection of any set with the empty set is the empty set. And also note that a union of any set with its complement is the universal set. An intersection of any set with its complement is the empty set. Idempotent laws. A union of any set with itself is that set. An intersection of any set with itself is that set. Complementation law. We complement the set twice, will get that set. Remember, the complement of a set A is the universal set minus A. So complementing a set A twice, it means we are complementing the universal set minus A, which is the universal set minus A. That's why we'll get back that set. Commutative laws. A union B is B union A. A intersect B is B intersect A. Then associative laws. Associating the brackets. This is what is happening. Can you see? It's just about moving the brackets. Distributive laws. A intersect into B union C can be written as A intersect B union A intersect C. And also A union into B intersect C can be written as A union B intersect A union C. Lastly, De Morgan's law. The union changes to intersection when complemented, and the intersection changes to union when complemented. So the complement of A union B is the same as A complement intersect B complement. And also the complement of A intersect B is the same as A complement union B complement. You will understand this one much better using a Venn diagram. So this whole part is your A union B. So when we complement it, it means we remove this part from the universal set. So we'll be left with A complement intersect B complement. And that's for De Morgan's. And looking clearly at this Venn diagram, A union B is the same as A intersect B complement union A intersect B union B intersect A complement. Where this part is A only and this one is B only. So they are called the difference. A only, A intersect B complement, is denoted by A slash B, which is A minus B, is defined by a set that X is an element of the universal set such that X is an element of A intersect X is not in B. And B only, which is B intersect A complement, also denoted by B slash A, which is B minus A, given by a set that X is an element of the universal set such that X is in B intersect X is not in A. So A only and B only are the differences. And the union of A only and B only is called the symmetric difference. The union of two disjoint sets. So the symmetric difference of two sets A and B is denoted by A bulb B or A triangle B, which is the same as A union B minus the intersection. It's also the same as A union B intersect the complement of A intersect B. So looking at the Venn diagram, the symmetric difference is this part of A only union this part of B only. So, but you know the whole part is the union. So if we remove intersection from the union, we're left with the symmetric difference. And this explains this. And one another thing. Do you see that set A is nothing but A only union A intersect B, and set B is nothing but B only union A intersect B, and this is clearly indicated on the contingency table. This is the table I'm talking about. So you can see that you are having your set A and A complement, your set B and B complement. So this is from the Venn diagram, right? So your set A is given by A intersect B union A only. So which is this, as you can see here. And your set B is given by A intersect B union B only, which is given by this, as you can see. And for your A complement and B complement, A complement is given by B only union complement of A intersect complement of B, which, as you can see here. And B complement is given by A only union complement of A intersect complement of B, as you can see here. A complement intersect B complement is just the complement of A union B, by De Morgan's, which is defined by X an element of universal set such that X is not in A intersect X is not in B.